Unit Operation Classroom. Um, my name is Shekhar Bhattacharjee, and today we are discussing a problem on dependence of equilibrium constant on temperature. For a reversible endothermic chemical reaction with constant heat of reaction over the operating temperature range, certain temperature range, K is the thermodynamic equilibrium constant. Which one of the following figures uh, shows the correct dependence of K on temperature T? Okay. So this is a very standard Van 't Hoff's equation. We all know this one right here. And we know this delta H zero reaction is a standard heat of reaction at the temperature 298 Kelvin. And this, of course, is defined as this summation of the heat of formation multiplied by its stoichiometric coefficient. This is a very standard equation. So here we see here the natural logarithm of k is plotted against 1 over t, and we have to find out the slope. So really we have to find out the slope of this one right here. So how do we do that? This is just a little mathematical manipulation here. So let's assume x is equal to 1 over t. So that's a derivative of dx over dt. So I can write that as in for from the chain rule, this one right here. And of course, this one is given by this Van 't Hoff's equation, and this one we have seen. This is right here. So it comes here. So the slope is negative of delta H zero reaction over R. Okay, so that's the equation from Van 't Hoff's equation. And the slope of when you plot natural logarithm of k against over 1 over t, that's going to be the slope. Since delta H zero reaction is constant, we are assuming not the temperature dependence of this delta H zero reaction, and R, of course, is the universal gas constant is constant. So this would be just a straight line with a negative slope. And as you can see, A it fits that particular definition. This one, of course, is a straight line with a positive slope. This is not correct. This is a curved nonlinear function. We don't know what kind of function. So anyway, that is also not true. And this is a parabolic, so that is also not true. So this is the correct option. Okay. Um, Okay, why? Again, let's see, for an endothermic reaction, we know delta H zero reaction is positive. And so if that is positive, so this is going to be negative. That's what we said. So A is the correct option. Let's quickly see why it is so. From a different perspective, if the 1 by T, if we decrease this value, so if we go on this one, that means, of course, the temperature is increasing, right? So if with increasing temperature, that means if we go along this direction, as you can see, the value of natural logarithm of K is increasing. That means the value of K is increasing. So for an endothermic reaction, as the temperature increases, K increases. And for an, of course, exothermic reaction, as the temperature increases, K will decrease. So as we said, so this is the one, and of course this is the correct option. Quickly, okay. First of all, just I wanted to say that read a good textbook to build your concept. These videos are not enough. Um, we are going to use La Chatelier principle, which we know that when a system at equilibrium is subjected to a change, temperature, pressure, or concentration, the system adjusts itself to oppose the effect of the change. So this we already know that and restore a new equilibrium. So how does that apply to this particular problem? For an endothermic reaction, we can write an endothermic reaction as this. That means the reactants, and we know absorbs it, so we have to supply heat to the system to carry out the reaction. So reaction plus heat is product. So that is basically an endothermic reaction. Huh? So if we increase the temperature, that means we are adding heat to the system. So if we add heat to the system, what the system will try to do, it will try to absorb that extra heat which you are adding. Initially at equilibrium, now we are adding heat, that means we're increasing temperature. So it will try to do what? It will try to absorb the heat. How can it absorb the heat, extra heat we're adding? So by converting the reactant, so by carrying out this reaction in this direction, so that way heat will be consumed. So that means more and more of the products will be formed. Okay. And we know that the equilibrium constant, of course, is a ratio of the product of the activities of the products raised to their stoichiometric coefficient, and activity of the reactants raised to the corresponding stoichiometric coefficient. So if this increases, so that means this K must be increasing. So that's K is. Therefore, for endothermic reaction, as temperature is increasing, K will increase. So this will also increase. So it's the same thing as we see that as temperature increases, 1 over T value decreases. So as we keep on going, we see that the K increases. So this is the correct option. So from both standpoint, quantitative and both from qualitative, that means the Losch-Thiriot principle, we see that option A is correct. Now you may stop the video if you want to, but I'm going to discuss more of the application of this problem to process industry application. Let's quickly look into the steam reforming of methane, which supplies, of course, hydrogen to ammonia plant. Very quickly, what it is, we use natural gas, which is primarily we know is methane. So first we do the desulfurization. We remove the hydrogen sulfide and mercaptans, which of course are the poisons to the reforming catalyst. So this is the very first step, and it goes to my steam reforming reactor. As you can see, it's kind of really high temperature, 20 to 30 bar, also high pressure. And what the reaction is, the methane, as we said, this is natural gas, primarily methane, reacts with steam. So we are supplying steam. How? Again, we burn the natural gas in a boiler, and we get the steam, and we inject the steam here. So methane reacts with steam to produce carbon monoxide plus hydrogen, a good amount, 3 moles of hydrogen. And this is an endothermic reaction, and we have nickel catalyst. Okay, so here from the output, as you can see, we have carbon monoxide and carbon dioxide, unreacted methane, and the hydrogen. So next we have the shift react water gas shift reactor. There are of course two types: high temperature shift reactor, low temperature shift reactor. But very in general, what happens in the shift reactor? This carbon monoxide is further react with the steam to produce carbon dioxide. Carbon monoxide, of course, we need to remove from the system because this is generally a poison. So it removes carbon monoxide, and so the shift reactor purpose of the shift reactor is to remove the carbon monoxide and convert that to carbon dioxide and produce more hydrogen. Okay. And then, of course, it goes to a pressure swing absorption unit, and where we get a very pure hydrogen, 99%, and that goes to my ammonia plant. Hmm. So again, if this this is an endothermic reaction here. This is an endothermic reaction. Hydrogen yield, of course, depends on the value of K, so equilibrium limited. So as we increase for endothermic reaction, we know as we increase the temperature, K value increases. So reaction is so if to get a good yield of hydrogen, of course, we need to have as high possible of temperature. So the temperature, the reaction is carried out at a pretty high temperature. 800 to 900 degrees Celsius, but we really cannot go beyond that. So we have to do some kind of optimal temperature. Why? Because if you go to high temperature, there will be a high fuel cost, and of course, the material construction becomes is a constraint at high temperature, and it also shortens catalyst life. If you reduce the temperature, let's say to 600 degrees Celsius, the K is too small. So we really decide on 800 to 900 Celsius and then the pressure. Okay, so as you can see, there's an application of this particular problem, what we had discussed before, to an actual industry problem. A similar problem, uh, look at the Haber's process. Okay, in the Haber's process, we know it produces ammonia. We all know that. So what happens? We have a furnace here, and of course, it can be natural gas fed furnace. So here's the steam reforming reactor we just discussed. This is a primary reformer, 800 to 900 degrees Celsius, 20 to 35 bar, and it's an endothermic reaction, which is discussed in the previous slide. Okay, so from here, then we go to the secondary reformer. So from here, it goes to, so we have unreacted methane, steam, carbon monoxide, and hydrogen. That goes to the secondary reformer. And what happens? It carried out at pretty high temperature, 1000 degrees Celsius. And this additional heat and this also supplies nitrogen, because the reaction is methane is partial oxidation. That means we introduce oxygen, and of course there's a large amount of nitrogen comes with the oxygen, because we are injecting air, and it produces more of carbon monoxide and more of hydrogen, right? So from this, so here's the air going in here and from here. And of course, we'll have a good amount of nitrogen, hydrogen, and carbon monoxide. Okay. And of course, unreacted methane. And then, of course, there is a waste heat boiler to take the heat out, and that produces steam that goes to the steam header. Next, it goes to the shift reactor, which also we discussed here, right here, the shift reactor. Okay, so in the shift reactor, what happens? We know that carbon monoxide reacts with the steam and to produce carbon dioxide and hydrogen. Okay, so this is a mildly exothermic reaction around 500 degrees Celsius, 20 to 40 bar, iron oxide, chromium oxide catalyst. Okay, so now we have the good amount of carbon dioxide. Carbon monoxide is almost converted. We have nitrogen and hydrogen. Next, of course, we remove the carbon dioxide. This is a very standard one, amine removal. So we inject amine to remove the carbon dioxide. So from here, as you can see, there will be some amount of carbon monoxide and very little amount of, and some amount of carbon dioxide, and primarily nitrogen and hydrogen would be here. And they now come to the methanation reactor. What is the purpose of the methanation reactor? Because we do not want carbon monoxide and carbon dioxide to go to my ammonia plant. Okay, that's harmful. But methane is not. Methane is not really harmful. So we convert this carbon monoxide. It reacts with hydrogen to produce methane, and carbon dioxide also produces methane. This is a highly exothermic reaction. So this is called the methanation reactor. Typically 250 to 300 degrees Celsius, 20 to 30 bar. So once that, so we basically carbon monoxide and carbon dioxide are removed. So we have hydrogen, nitrogen, and of course methane and argon. And then of course it goes to the Haber-Bosch reactor. And this is a very standard reaction which you all know. This around 450 produces ammonia. This nitrogen and hydrogen reacts to produce ammonia. And we have 450 degrees Celsius, 300 bar, and we have iron catalyst, and it's an exothermic around 92 kilojoule per mole. So for an exothermic reaction, we know if we increase the temperature, the K value will decrease. So what happens? But we need a certain amount of temperature. Why? To have a reasonably good kinetic. So rate of reaction. Okay. So how do you handle this? That the lower value of K, we try to compensate using high pressure to offset the low temperature constraint. So anyway, so what you have seen is that there's a great amount of application of this particular problem or this particular concept to actual process industry. So I stop here.